A geometric sequence is similar to an arithmetic sequence in that it does something to get from one term to the next that is a consistent operation. In an arithmetic sequence, we had a common difference, or maybe a common sum, if you want to think of it in terms of adding the same value to go from one term to the next. In a geometric sequence, now we're going to be multiplying by the same amount to go from one term to the next. So A1 is still called the first term in your geometric sequence. And R, this time we don't have D, that wouldn't make any sense. R is now the common ratio. And this is the amount that you are multiplying from one term to get to the next. This is the same amount. So maybe multiplying by 2 or multiplying by -1/3 or whatever that common ratio is to go from one term to the next. That makes your series geometric. The first term, in general, I'm going to call this A1 again. There's no sense in using a different variable. So A1 is just the starting point, all right, the starting value, the starting term value. A2 is going to be found by using the value A1 and then multiplying by R. Remember, R is that common ratio. R is how much you want to multiply by each time. Therefore, the next term is going to take the previous term, A2, and multiply by R once again. Now, A2 was already A1 times R. So now we've got A1 times R squared altogether, right? It's just kind of like, this would be A1 times R, but then times R again, which is A1 times R squared. Okay, so this pattern continues all the way down to the end. For the nth term, we're going to take the previous term, which already contained a series of r's, n minus 1 r, n minus 2 r's in this case. But now we're taking that quantity and we're multiplying it by r once again, which gives you r to the power n minus 1. Okay, so the power that we have is always one smaller than the term number that we're working with. So this power that we're going to work with, that we're going to end up with, is going to be one smaller than the term that we're trying to write down the value for. The nth term in a geometric series is equal to A1 times R to the n minus 1, and that formula is on your formula sheet. We do have to specify that using 0 wouldn't make sense. So therefore, any value of R is okay, except for 0. Positives, negatives, fractions, decimals, but just not 0. Otherwise, you would just have a bunch of zeros, and that's not really anything that's interesting. To show that a sequence is geometric, and once again, I would recommend putting this on your formula sheets, just like you did for the previous section. But to show that your sequence is geometric, you're going to show that the ratio of an divided by an minus 1 equals this common r value. And when we're showing this, as you'll see in that example, every single term that involves an n will cancel out, leaving you with just a constant, and that constant is your r. The sum of a geometric series is here. Specifically, it would be when you're adding up all of the terms that you see listed right there. And so that goes right there. So we're adding up all of those different term values, creating a series. When we get our final sum, now it's a series. And this is going to go from k equal to 1, that's the first term, all the way to the end, the nth term. So k equals n. And that's how you would write out all of your terms if you wanted to see what they look like individually. All right, but this is a much more convenient way of finding the sum of all of those n terms. And that's on your formula sheet. And r, not only is it not allowed to be 0, it cannot be a 1 either. Otherwise, it's just the same number that keeps repeating itself, and that is not interesting either. Does the geometric series converge or diverge? Brand new information. It does not make any sense to talk about converging and diverging series with regards to arithmetic sequences in the previous section. They will always diverge, always and always, okay? Because you keep adding more and more to your quantity or subtracting more and more from your initial quantity. And so then your series would never just stop and not get any bigger or not get any smaller. But when in the case of a geometric series, it is possible for your series, which again is your sum, right, this total sum, to just stop accumulating value. All right, and if it stops accumulating value, we say that the series converges to whatever value you end up at. Okay, but if you keep adding, or sorry, if you keep multiplying by a particular number for your common ratio, and the term values either keep getting larger and larger and larger, or smaller and smaller, more and more negative, and they never get close to zero, is what I'm trying to say, then you keep adding and subtracting more amount to your overall sum, then in that case your series diverges. All right, I hope that makes sense. So diverges means that the sum goes to either something big or something very negative. And if it's going to converge means that the sum goes to a particular number that you can see. And the way we know if your series will converge or diverge has to do with your value of R, the common ratio. If the absolute value of R is less than 1, then that series will converge to the amount A1 divided by 1 minus R. And that is the last thing that's given on your formula sheet for this chapter. So the question might say, here's a series, and here's the first term, and here's the common ratio. And what do you think is going to happen if I add up an infinite number of terms? Right? Because n goes to infinity, right? The series does not stop. It keeps going forever. And so if you get the series total sum and you will converge to a particular number, that means that once you get so far down the line in these term values, they're not really getting any different. They keep looking more and more the same. And in fact, they keep getting closer and closer to zero is what's actually going on. And so if you keep adding term values that are practically zeros, you're not increasing your sum at all. And your series has stopped growing. And therefore it converges to whatever that value is. And this is what the value is. Here we go. First of all, we're going to show that the sequence that we have given in front of us is geometric. Prove that it's geometric. We're going to prove that it's geometric according to that statement right there. All right, so we want to show that an divided by an minus 1 equals r. All right, in this case, it's called d. So we want to show that d n divided by d n minus 1 equals r. Okay, so dn is exactly as it was given to you in the problem. dn is equal to 3 to the n over 9. And if you wanted to write out dn minus 1, what would that one look like? And so remember how it's a function. And so you're going to replace the input is right there, with the new input, which is now going to be n minus 1. So that n minus 1 goes up there in the exponent in place of the n. So this is 3 to the n minus 1 over 9. So now we're going to make a ratio out of these two pieces. dn over dn minus 1 equals 3 to the n over 9 divided by 3 to the n minus 1 over 9. And now you simplify, right? Simplify. So it's the top fraction divided by the bottom fraction. And we divide fractions by taking the reciprocal of the second and multiplying it by the first. And these 9's cancel out. And we multiply straight across the top and straight across the bottom. And we have the same common base on top and bottom now. 3 is the common base. And so when we're dividing the same base, we take the top exponent minus the bottom exponent. Top exponent, which is n, minus the bottom exponent, which is n minus 1. And that is now 3 to the n minus n plus 1. And that is now 3 to the 1. And you're done. This is r. That's your common ratio. All of the n's canceled out. They are no more. And so the common ratio is 3. The first 4 terms that you were asked to write out, d1, would be 3 to the first over 9, which we can reduce to 1/3. The second term, d2, is 3 squared over 9. We'll call that 1. The third term, d3, is 3 cubed over 9, and we should get 3 out of that. and D4. Remember how the common ratio was 3? Common ratio is 3. I should be multiplying by 3 for each of these answers from the previous answer. And so if I write it out, though, using the formula 3 to the 4th over 9, and that equals 9. So I'm good. Those are the first 4 terms.